brief introduction. So welcome everybody to today's seminar, and it will be actually a colloquium level talk by Jim Libby, our colleague at IIT Madras, and he's also a spokesperson for the Belle II experiment, if I'm not wrong. Are you right?
No,
Jim?
no. I'm a member.
A member.
But I'm not the Tori Imajima is the spokesperson. We only have one. So.
Okay, he's a member of the Belle II collaboration, and also other.
But thanks for the promotion. That's.
Okay, and yes, and also other experiments, and today he will be talking to us about this new exciting B-anomalies that have been that has become more and more convincing. And he will try to convince us today that it is indeed not something that will change physics in the future. So over to you, Jim.
Okay. So thank you, Ayan, for the invitation and the introduction. So I will be very much focusing on the experimental side of these anomalies. I will at times touch upon the phenomenology as well, but really what was the genesis of this talk and much of the recent excitement is this paper from LHCb related to a certain type of B decay, which I'll describe in some detail as we go through.
Jim, may I interrupt a little? Somehow the whole of the slide is not being visible at one. Are you intending it that way?
It is to me. I don't know what's missing.
There is this stripe in the right-hand side, but I think it's deliberate with which also gives the that one. Yeah, that's part of your format.
Yeah. So
okay.
The aspect ratio.
Okay.
Let's see.
Let's see.
You cannot. I guess the problem is if you can't see the axes labels or anything at the bottom.
Yes, indeed. Yeah.
You can't see?
No.
No. Now it is. But previously, I think when we are scrolling up a little, a part of the slide was not visible. That's all.
Okay. I'll continue.
So I'm just wondering if. Yeah.
I don't know what to do. This is usually what I do with PowerPoint, and it's normally fine. Okay, let's see how we go. If there's a problem, let me know, and I can potentially make a PDF or something, and it may be better. Okay, so I'm going to do an overview, and I'm going to make some references to Dickens throughout this, and you'll see why when you get to the conclusion. But essentially, I'll begin with a very brief introduction about B-anomalies in the past. And I'm being rather generic in how I interpret B-anomalies here. This is really about flavor physics and the important role it's played in the development of the standard model. And then, like Scrooge, we will move on to the B-anomalies of the present. And in particular, I will review the measurements, some not quite as recent as the one that's highlighted from LHCb this year, but there's a whole pattern of measurements that need to be discussed when you talk about the B-anomalies. And then I'll talk a little bit about the phenomenology that may describe these. And then I'll refer to some of the other anomalies that are getting press as well at the moment, most notably G-2. And then I'll talk about the B-anomalies in the future, which essentially is talking about two experiments. I'll be very brief on LHCb, though they're the ones that are driving a lot of the measurements that we see today. But I'll talk a lot about Belle II, which is what I work on principally. So hopefully it won't be as a distressing experience as this for you, but we'll see how we go. All right, so such a talk would always begin with the standard model. And what I'm going to be talking about today is the weak interaction amongst the quarks. That's really what flavor physics means. And this paradigm that we have in the standard model of three generations, three forces, local gauge invariance leading to the force carriers, and then ultimately the masses explained by the Higgs boson, has been extremely successful over 40 years since Glashow, Weinberg, and Salam proposed this. So successful, in fact, that it's been awarded, I think, roughly 14 Nobel Prizes for different aspects of this. And many of these are clustered around what's here in the flavor sector and also in the weak sector. And I will talk a lot about how not a lot, but I'll introduce how the standard model was built up from some observations coming from flavor. But of course, we know this is not the whole story. I don't want to repeat the usual things that are said, that there are obvious problems with the standard model. There's no dark matter, and then there's various aesthetic problems related to fine tuning and this 3-generational structure not really being clear why we must have that. Why not 4? Why not 5? And the goal has been in collider physics is to try and find measurements that would disagree with this picture. So first, I'll just do my history and talk about flavor physics, because it really emphasizes the role that it plays when we're looking for new physics in these types of measurements. So several aspects of this standard model that I just showed you came about through flavor predictions. Probably most famously is the Jim mechanism, whereby the suppression of this neutral kaon decay, the K long to 2 leptons, was resolved by Glashow, Iliopis, and Maiani by suggesting that one extended the Cabibbo mixing that was there amongst the up, down, and the strange quarks to add a 4th quark, which naturally led to a cancellation that would suppress this rate. Then Kobayashi and Muskawa actually took this further and realized that one could get CP violation within this quark mixing matrix if you extended it to 3 generations. And this was even before the charm quark was discovered. So they predicted the top and the bottom quark, ultimately a 3rd lepton as well in the tau. And this, of course, turned out to be the correct paradigm. But it also emphasizes one of the issues that one has with the standard model is that we really do not understand the numerical values that go into the 4 parameters that describe this matrix. There's a strong ranking of the elements here, where if you couple together the 1st and the 3rd generations with VUB and VTD, the size of those elements is much smaller than those on the diagonal. So where this structure is coming from is one of the understanding problems of the standard model. But one I'll just highlight here before moving on to the rest of the talk is B mixing and how it predicted that there must be a heavy top quark. So in 1987, the Argus collaboration, which was really one of the first original B factories operating at the Upsilon 4s, producing pairs of B mesons, discovered the B meson oscillations. And the signature for this was to see semi-leptonic decays of the B, which are the predominant decays, where you have like sign dileptons. So here you have a muon of positive charge and another one on the other side. And this is a very nice signature. And also this picture emphasizes something about E plus E minus collisions producing pairs of B mesons, which is what we do today at Belle II as well, that one has a very clean, pristine environment in which to study these decays. Now, the mechanism for B mixing is dominated by this loop process, whereby you have W's and top quarks in the loop mediating this. So this box diagram, which is basically changing flavor by 2 units, because you have beauty of 1 and on the left-hand side, the initial state, and beauty of -1 on the final state. So it's changed by 2, these delta F equal 2 transitions. And the rate at which they observed these type of events predicted that the mass of the top quark had to be greater than 50 GeV, and it then took another decade or so to actually discover this at the Tevatron with a mass of 175 GeV. Simultaneously to this, like most things, it had already been discovered at UA1 and UA2, or UA1 by Rubier and others, and this is a headline from the New York Times from 3 years earlier that said they'd already found the top quark. So what I'm saying here is that these precision measurements in B physics have helped predict other features of the standard model in the same way that the Higgs was predicted from precision electroweak measurements where its mass might be roughly. And also B mesons with masses of 5 GeV are probing mass scales an order of magnitude higher than its own mass. And this is really what we're doing today, is we're using such processes to try and understand mass scales at a much higher value than the B quark mass, which we can do through these types of precision measurements. So this has played an important role in us understanding the structure and the hierarchy that's there in the standard model as we've gone through over the last few decades. So this is a nice slide that I've stolen from a talk we were given on Belle II after the recent anomaly announcement from LHCb by Andreas Krevelin, who's one of the people who works a lot on B2S mu mu. And basically what we do is a simple flow diagram that we make our measurements, and if they don't agree with the standard model, there must be some new physics. And this complements what's done directly at the LHC. At the LHC, you have 14 TeV of energy, and you can make massive particles of the TeV scale potentially. And through the last 10 years, 12 years, they've been successively setting as good a limit as possible on these types of new particles, whether they be supersymmetric or otherwise. But they are limited by that center of mass energy to make these direct discoveries. Whereas if you look at precision measurements of flavor variables, so this shows some here in the quark sector, this BS to mu mu and epsilon k related to CP violation in the kaon sector, as well as lepton number violating decays of muons, you are actually probing mass scales, or you can probe mass scales that are very much higher than what you're working at, because you have very strict limits on what can actually be happening in these loop processes that will mediate these decays. So this is an indirect search for new physics. Now, as you'll see as we go through, the drawback of this is it's not necessarily obvious what the new physics might be, and I'll talk about both.
Jim, can I ask something?
Sure, sure.
So, so your point is that somehow this B quark oscillations and this B mesons give a very clean environment. So it was not quite clear just from the properties of, say, the tau lepton or something, what should be the mass of the top quark B. But from this you could get a clean estimate. Is this?
That's correct. So, sorry, just going back to this. So this box completely drives the rate or the mass difference between the two CP eigenstates, and that tells you the rate of B oscillations, and you can interpret that as a limit on the mass. It has to be heavy. I can't remember exactly. I think it said quadratic dependence, but I can't remember. And so the limit's a little loose as you go to higher masses, but it must be of a certain. You can't be too light, otherwise the rate would have been much slower. So this relatively fast oscillations told us that the mass of the top had to be quite heavy, and that's what it does. It's all these kind of precision measurements that are looking at loops allow us to make some constraints on what the unobserved particles in the loops might be. It influence the observable that we see. And that's very much the story of what we do now.
I see.
Okay, so this is the idea, and we like to refer to it as being complementary, because if you see a direct signature at the LHC, that's fantastic, and it's a very clear observation. Whereas if you're seeing deviations in a variety of measurements, it's also good, but the interpretation is not so straightforward. Okay. So that's something else you must bear in mind as we go forward. So the one here that really matters is this BS to mu mu, which I'll start to talk about when I get to the present observable measurements. So this now brings me to the meat of my presentation. You can look at this quote, which I've paraphrased from Dickens, telling you maybe the beginning and the end of most books, and maybe talks are probably the easiest things to look at, but this is, I'll move on to my main course now. So I'll talk about the present. And there are really two types of anomalies in the B sector, and they're related to two types of processes. And it's quite important from the beginning to understand what the principal differences are between them. So this BS to mu mu or BS to LL type of diagram is a flavor changing neutral current where you have a B quark transforming to an S quark. And this can only happen via a loop process in the standard model. The Z does not couple between generations. So you need to have this penguin loop, which I'll mention a little more about on the next slide, or you will have this box diagram where you have W and a neutrino, or you have the top quark, Z0 and photon here. So again, you're sensitive to all these different particles in the standard model within these diagrams. But the lesson is that perhaps we can substitute some of these particles with ones beyond the standard model and alter the observables that we see in these types of decay. So this is this loop process, which I'll talk more about in the next slide. But there is another type of anomaly, which is referred to, which is happened in actually the most common type of B decay, which is in a semi-leptonic decay. But it's the first time in the last decade where we've actually measured tau leptons in the semi-leptonic decays. And these rates have found to be somewhat anomalous compared with what's expected when you look to semi-leptonic decays, where you have a muon on an electron as the lepton in the final state. So this is the most straightforward and most favored type of B decay, has a branching fraction of around, I think it's 11%. I should remember that. Now, there are pros and cons with these. Now, these loop diagrams are great for the reasons I've already mentioned, that within these boxes, you actually reach mass scales that are very much higher than what you can probe directly. Whereas with this tree level diagram, if you're going to modify this with some new physics, that new physics has to be approximately around the mass scale we're already probing. So you then have to find ways to describe why we haven't seen this already in our collider searches at the LHC, for example. So that's about the mass scales probed, and that means the interpretation is somewhat more difficult for the B2C tau nu than these loop diagrams. And then there's an experimental difference between these types of anomalies, which I'll go through, that this B2C tau nu has essentially been seen at some degree by 3 different experiments, whereas LHCb is the only experiment with precision currently to be able to say something meaningful about these BS to mu mu anomalies. So a gold standard that we have in experimental physics is if you can corroborate your measurement by more than one experiment. That reproducibility by another experiment is not yet there with the B2S mu mu anomalies. So with that said, I'll talk more about this B2S LL or B2S mu mu, as it's what LHCb has measured. And the prototype for this, and the most interesting, I think, is this B to K star LL, where your strange quark is hadronized into a vector meson. And you have this penguin loop diagram is the dominant one, as well as the box. And here's John Ellis, who came up with the term penguin. I suggest you research. It's a rather amusing story as to how he came up with the name penguin. It was losing or winning a bet, losing a bet. He had to get the word penguin in his next paper, and he managed to dream up that this diagram somehow looks like this. Now, what's so nice about this K star LL is that there's a 4-body final state, and that means because the K star decays to a kaon and a pion, you end up with many differential distributions that you can measure, which are very sensitive potentially to interference, which may not alter the total rate that you might have, but could alter significantly these differential distributions. And history again tells us something here, that if you look at the forward-backward asymmetry for E plus E minus to dimuons, for example, the overall rate is largely unaffected by the gamma Z interference. But if you look at the forward-backward asymmetry, there's a very large effect, even a long way from the Z mass. So this is what we're doing with these types of decays. And also there's another degree of freedom that one has in that the dilepton system and all the measurements are parameterized in terms of the invariant mass of this dilepton system. So here we're looking at the differential rates as a function of this invariant mass of the dileptons. And there's a rich structure here. There's a very low mass peak, which is related to the photon pole that's here. And then you have these two peaks, which are not actually loop diagrams. They're related to decays of the charmonium system. And these are tree level. So these actually cause theoretical issues, but experimentally are hugely useful because they're high rate control samples that we can use to calibrate the measurements. And then there are different regions. I'll talk more about these C9s and C10 parameters. These are Wilson coefficients, which are a way in effective field theory of parameterizing potential new physics contributions. And again, in different regions of Q squared, you're sensitive to different potential new physics operators. So this is a very rich phenomenology that's there in these types of decays for you to be able to study possible new physics effects. So just to define the nomenclature here, because I'm going to show you the first anomaly, which has got a rather odd name, and it has to be defined in some way. So you've got this four-dimensional differential distribution, which is in terms of Q squared, and then the decay angles of the K star. So here you have the rest frame of the B, then you have a direction defined by the back-to-back motion of the K star and the dilepton system. And then in the rest frame of the dileptons, you can identify a decay angle with respect to that direction. And similarly, you can do that for one of the particles flowing from the K. And then there's some angle between the two decay planes. So with these three angles coupled with the Q squared, you can parameterize the decay. And this is this expression here with these various dependencies upon these different angles. Now, I'm just going to highlight here this S5 parameter because that plays a role later on, and you can predict all of these within the standard model. And a lot of work has gone on to defining observables that have minimal theoretical uncertainties. And one way of doing this was to sort of normalize them in some way or divide through by other parameters. So dividing through by this combination of this FL, which is the polarization fraction, longitudinal polarization fraction, you get a relatively robust theoretical prediction for these measurements. And this is P5 prime. So moving to the next slide, this is the first.
Jim, sorry,
yeah.
Can I interrupt you?
Sure.
About your previous slide.
The
slide before this. Yes. So maybe you're going to talk about it later, but I'm very curious to know. So you said that in this Q square space itself, you get a lot of this sensitivity to higher dimensional operators. So are some of these really interesting in the sense of they violate some standard model symmetries or have some very good signatures, or some of them could be more interesting than others?
I think so. For example, this region which has dominated by this B to S gamma transition, because we actually measure B to S gamma rather well already, this is probably considered somewhat less interesting region than the region that lies in between that and the J psi peak, where you have this interference between these two different four-quark operators. And I'll show you why this region is in particular interesting. And then the higher Q squared opens up some different potential operators, the C10 operator, which I won't talk about so much in the future. But then there are long distance CC bar rescattering effects, which are somewhat harder to control theoretically. So there's different theoretical problems here. So ideally, you'd see a pattern of some regions either agreeing with the standard model, not agreeing, or all regions not agreeing. And that will tell you something, because you'll mean that different four-quark operators are influenced by new physics. Okay, so either one is 2 is, 3. You don't know until you make all the measurements. Okay, so that's the reason why it's interesting to divide it up in this Q-squared.
Okay, thanks.
Does that answer your question, Ian?
Yeah. Okay, thanks. So you're saying the four quarks operator sector can be probed at least by this.
Yeah.
By this.
Yeah. And I will show this in a bit when I come to the interpretation. Okay. Okay. So yeah, I'd introduce this rather ungainly nomenclature that's there to measure these differential distributions. And now the measurements themselves came in 2016, so it's about 5 years ago now. But this is the paper where this P5 prime variable was proposed. And this very messy plot, you should focus first of all on these black points, which are the LHCb measurements of this P5 prime variable, which is this coefficient of this angular distribution. So they fit this angular distribution or this four-dimensional distribution and extract these coefficients and then just measure them as a function of Q-squared. And there's this run of points lying between this photon region and the J psi, which are all well above the standard model predictions, which are given here in orange and purple. And this depends on which hadronic parameters you're choosing. You can decide how you want to parameterize your hadronic form factor, which is an unknown, and this is consistently high. Now there are other measurements coming from Atlas and CMS and also from Belle, but they do not have the statistical precision, and it's all rather messy because they choose different regions of Q-squared to make their measurements. But you see Belle and Atlas and LHCb are consistently high. The CMS fluctuates downwards. They seem to agree with the standard model. But given all the precisions, and I'll show global fits later on, essentially this comes out to be more than a 3 standard deviation from the standard model. But because of the theoretical uncertainties here, combined with the fact that it's not as clean a measurement as some of those that I'll show later on, this is extremely interesting and has been for some time, but people are always unsure about whether it's the theory or there's only one measurement. But LHCb have done a very thorough job with this, and you see, referring to my answer to your question, that at this high Q-squared there seems to be good agreement between the data and the standard model prediction, and it's just in this interference region, which would then be telling you something about where the new physics might be in terms of the operators. And you'll see that when I show the fits a bit later on. But there's an important point moving to the experimental side of things here, that this is just for muons. And so it's a good time, given there's probably not a huge amount of familiarity with it, to discuss the LHCb experiment in a single slide, but I'll just explain why it's the case that they're just looking at muons here. So the LHCb.
Hello, Jim.
Hi, is that
Hi,
Srihari?
Yes, hi, Jim.
Hi.
Can I ask you a quick question on that previous plot?
Sure.
So I was just wondering, it seems like there is some tension between the LHCb and the CMS data, is there not?
Yes. But when the global fits are done, and I'll show you the results of that later on, given the limited statistical precision of CMS compared with LHCb, it doesn't lead to a very large pool that's a problem for those fits. So there is some tension, but it's of the order of 2 standard deviations. It's not more than that.
Yes,
when you put everything together. So it's not significant at the moment, but bear in mind there are going to be much better measurements, particularly from CMS, at some point in the future, because they've got this large parked B data. So it'll be interesting to see how that develops. Now, I'm not an expert on these measurements. I know the LHCb people feel that they may not be quite as robust as in some of the things that they've taken into account. But I wouldn't want to speculate further on that. I think that's only time will tell when there's more information.
Yeah, I guess, it gives one pause because CMS seems to agree with the standard model prediction. So I don't know if it counts for something, but
Yeah, but then on the flip side, Sri Harry, you can look at the Atlas point and say,
that's
well,
right.
yeah, so
Fair enough, yeah.
I don't, that
Well, if you're a conservative and if you want to take a conservative view, then you would focus more on the CMS agreeing with the theory prediction.
okay, well, I'm a frequentist, so each point is only as good as its error bars. So,
Okay. All right.
yeah, so
Okay.
I'll show you
Thanks.
the global fit, and there I think it's convincing that something is going on. All right, so,
Yeah.
but let's talk about the other observation, which, well, I'll talk about the experiment, then I'll talk about the RK and RK star. So LHCb is operating with these 13 TeV-PP collisions, and the reason for that is that in every 2 inverse femtobarns of integrated luminosity, one gets 1 trillion 10 to the 12 BB bar pairs. And they've collected so far 9 inverse femtobarns of data, some of it at slightly lower energy where this number would not be quite correct, but they have produced many BB bar pairs at their collision point and collected many of them. And they are a forward geometry experiment at the LHC. So the collision point is here on the left-hand side of the schematic of the experiment. And the reason for that is that the B quarks primarily get boosted into the high rapidity region, which is being instrumented here. So you get both B quarks within this acceptance. So this increases your efficiency further. There's also a huge advantage of having your B quarks boosted, exploiting the long lifetime that they have of around 1.2 picoseconds or so. It means that the vertex of decay of the B meson is well displaced from the primary vertex, and they can sort out background very readily using a high precision vertex detector that they have. So it's also there for time dependent CP violation, but I'm not talking about that today. That's an entirely different topic. But so this was designed from day one and gives it a competitive advantage over CMS and Atlas for doing B physics. And the other reasons for that are they have ring imaging Cherenkov detectors to cleanly separate pions and kaons over a momentum range from around 1 to 100 GeV, which is important for identifying final states of interest. And they also design their trigger just for B physics. So their full trigger bandwidth is dedicated to collecting not actually just Bs, they also collect charm quarks, charm decays very readily as well. But why just the muons is somewhat clear now, and if I show you an event display here. So they do their tracking with the dipole magnet. So you see the tracks are curved here. They get kicked as they go through the dipole magnet. But there are many of them. It's a PP collision. There is high multiplicity environment, even though they detune the luminosity at LHCb. So it's a very busy environment downstream here. And this red here is their electromagnetic calorimeter, which is extremely busy with lots of hits from photons produced from pi0 decay, for example. And then here they have the hadron calorimeter, which is largely used for triggering. It's not used for any energy flow type measurement that you might be used to from the other general purpose detectors. But these 2 purple lines here, these are the 2 muons. So they have this muon filter system where they have ion sandwich with then muon detectors in between gas detectors, and NWPCs and RPCs are there. And these allows them to identify high momentum muons coming from B decay very, very readily. And they can then track them through their precision tracking, and they'll get their vertex position. So this is a BS to mu candidate actually that I'm showing. But the problem is that to identify muons is highly clean, whereas this trying to identify electrons in this high multiplicity environment here is very hard. And that's why these angular measurements have not yet been made with electrons, for example, at LHCb. And I'll talk more about why that's important as I go through the talk. I'm going rather slowly here, so I need to speed up.
Jim, isn't the electrons overall some Q-square measurement has been done, if not the differential?
I'll come. That's the next couple of slides, so I'll talk about this. Yeah. So now I move to these recent measurements, these tests of lepton universality. So they're really updates of older measurements, but what's being measured here is just a ratio of the differential branching fraction as a function of q squared integrated over some q squared range. And this is done for both pseudoscalar and vector k star, done for both types. Now this ratio is extremely robust theoretically. It's very, very clean. It's got like it's 1 to a few percent. It's got very small theoretical uncertainties involved with it because the uncertainties to do with form factors just drop out in this kind of ratio measurement. It also has this control sample, which is coming from this B to S CC bar final state where you have a K or a K star with a J psi. And these are data plots. They look like Monte Carlo plots, but these are actually the data that LHCb have in these control modes where they can separate out these B decays using the lifetime, and then it's just whatever they see that reconstructed as a K star and 2 leptons is pretty much a B. But as you can see, the electrons on the right-hand side is a much broader distribution. And also the scales are different on these 2 plots. So it gets even more stark than this. So I've just borrowed a slide from a recent talk by Manuel Sevilla at the APS April meeting. It was in Pasadena. And here he's showing how hard it is to reconstruct these electrons at LHCb. So as I said, they had this dipole magnet. So as your electron goes through, it gets a big kick from which you actually measure its momentum. But there's also a significant amount of material, both in the silicon detector, the rich detectors. There's a vacuum chamber in which the silicon sits. So there's a significant amount of material, what we call radiation lengths, before the electromagnetic calorimeter. So there's a large chance of Bremsstrahlung. And these photons from Bremsstrahlung have to be added back in to try and improve your resolution. And in this plot here, it shows even with the best Bremsstrahlung recovery that they still have a long tail going to low values of the B mass because they haven't captured it all. There's a lot of energy lost. So it leads to a very broad distribution. And it also leads to problems trying to trigger because you lose PT or energy from these clusters and they're triggering on these eCal clusters. I can't go into the details of the trigger, but it affects their efficiency. So their efficiency is much lower for electrons than muons. So they have these double problems of efficiency and resolution being much worse. But they somewhat overcome that because they use this control sample and they take a double ratio. So issues with the trigger efficiency and largely the trigger efficiency and the reconstruction efficiency cancel out in these double ratios. And they measure this R parameter as this ratio of ratios essentially. So a lot of the experimental effects drop out. So this gives you significant confidence in the measurement because they have this control sample. No one would believe this if this was done on Monte Carlo, for example, but because they use this data control sample, it's quite robust. And then the 2 measurements they have, the new one is with their full data set. So be aware that they're going to update their RK star at some point in the near future, hopefully. It's been a long time coming. They stopped taking data in 2018. So these are the results. On the top is the RK. So this is where you have a K to mu mu or a K to EE. But you do see now when you have a much rarer loop process rather than the J psi, there is significant background underneath the electron signal at least. And then they have to understand this electron background. Some of it is combinatorial, which can be easily fit, but some of it is partially reconstructed decays of one type or another, and that's somewhat harder to model. But they've done a careful job, but they have half the number of electron events compared with the muons.
Sorry, a very stupid question. What is this x-axis here?
The x-axis is the invariant mass of the final state particle, so it should peak at the B mass. Okay, so it's just the B mass.
It's just mass. Okay, thanks.
Yeah, sorry, that's my complacency. I look at these plots. It's just the mass of the B. This is where primary plot that they'll always show when they're separating a signal. But it's also remarkably clean on the muon side. There's very little background. So these measurements all are low for the muons compared with the electrons. And this one that was released near Moriond is now the first one to creep over 3 standard deviations. And the standard model prediction essentially has limited uncertainty in comparison. So this is now a 3 standard deviation discrepancy.
Jim?
So, yeah, Srihari?
Yeah, so the JSI being used as a control sample. So you need to extrapolate a little bit out of the JSI region in order to make that RK measurement in this double ratio. But is that, like clean? I mean, there's no real, like uncertainties coming from there? No, that's under control. Yeah.
There are uncertainties. So if you see the systematics, the fact that the momentum distribution of the dileptons coming from the J side does not exactly match that coming from the signal, but you do all these corrections in bins of the momentum, right? So you break down that control sample to best utilize it as you can, but there is an uncertainty that comes from this.
But that's well
you're
understood,
right.
and it's like it's not a cause for worry or anything.
It's I think pretty well understood, but it is a cause for concern that, well, if something has gone wrong here. But I'd just like to emphasize that the electrons are actually, the electron mode completely agrees with the standard model prediction. It's the muons that are low.
Yeah.
So it's kind of, if it was the electrons were high, then you'd be like, yeah, maybe. But of course, this needs to be corroborated either by Atlas CMS or in the future Belle II.
Okay, thank you.
So all of these measurements can then be put together, and there's a big industry in doing these global fits. And there are now many, many observables because you have all these quadruple differential distributions in K star of mu mu in particular. But you can throw in everything coming from Bell, Babar, Atlas, and CMS, as well as from LHCb. And there's things like BS to mu mu, which is the same 4-quark operator involved. And you can then fit all of this in terms of different combinations of these 4 fermion operators. And this is always parameterized in terms of these Wilson coefficients. Now, what's shown here is not the Wilson coefficient for C10 and C9, which is basically V minus A theory here. This is just a deviation from V minus A standard model. This is a new piece which should be coming from the new physics. Now, if you fit all of these observables together, you get this blue region here. And if the standard model were correct, you'd get something here at 0, 0. And the authors of this paper say this is a 6 to 7 sigma standard deviation. And then there are assumptions in this. You're just using these 2 operators. But if you go and look at this paper, there are many permutations that they have, and many of them show significant deviation. But of course, you'll need more and more measurements to pin down which is the most favored. But this is one that's very clear. I think this has the best chi-squared of all of them. But I also want to emphasize the dominance of LHCb here. So LHCb is measurements alone is this red region, and all the other experiments combined are not really contributing very much to this global fit. So that goes back to what I was saying about that P5 prime distribution. So even though there are those points, because they're larger uncertainties, they mean they don't have very much weight when you do the full fit in the end.
Jim, again, can I ask something? So in this case, this O9, O10, will they also be important for some other processes, not say BDKs, like some Higgs three-body decay, like 2 photons, or I don't know, something simple, like some other kind of ways you can corroborate this operator?
So these kind of things are done in a way that they will escape other bounds, right? They're coming, but there aren't, the coupling of the B to the S quark, that's only coming really in these flavor observables, okay? So this is a 4-quark operator between the strange and the beauty quark that we're talking about here. Now, when you start talking about, which I think I do in the next slide, you talk about what your new theory might be if you're a model builder, then you have to worry about what that does in the top sector or the Higgs sector or whatever else. Okay. But this is just an effective field theory approach. These are the coefficients. These operators are the ones, if you deviate these a little bit, you can explain the data. And this is essentially just adding some more left-handed current. Very naively, this is what this is doing, this C9, C10 combination. So yeah, you're completely correct. You have to worry about other constraints, but that comes when you do the model building.
I see.
So just to also, if you take out the angular distribution, if you take out P5 prime, the significance weakens a little bit. It's like 3 to 5 standard deviations away from the standard model. So that P5 prime variable is really important for driving the incompatibility of the standard model with the data. But this, of course, is still very significant.
Just to ask again, so these two operators are special because they have coupling S and B, and
yeah, these are the only ones that can contribute to that BSLL process, right? So this is all we're looking at. This is all we can do in this effective theory, right? But you've got whatever the Lorentz structure is, you choose your operators, and you're effective Hamiltonian, and you get this. This is not saying anything about what the real driver of this would be. It's just showing you that this is what it's got to modify. Though there are many permutations for this. There are like 13 different permutations if you read the paper. Obviously, I can't go through all of those. So I'm going to get to the get back to my Dickens. This is poor Oliver Twist asking Mr. Bumble for more, and unlike him, you are going to get some. So there are more anomalies. This is going to these semi-tauronic decays now. Now this is tree level, as I mentioned before. So you have to think of either replacing the W with another charge mediator like a charged Higgs, which is common in extended Higgs sectors of beyond the standard model theories, or something I'll come back to is you can add a leptoquark that couples to both quarks and leptons, and this will potentially mediate the decay as well. And what's done here is, again, a very robust measurement theoretically, because you take a ratio between the tauonic decay and the electron and muon ones, and you can get very precise predictions for the standard model from this. Now, this is the oldest anomaly of all. There was a paper in 2012 from Babar that first reported the semi-tauronic branching fraction, and it's just been off ever since. But many other measurements have been made. So Belle have got several results on this. I'm just going to highlight how they do this because this is interesting for the second part of the talk. I'm going very slowly, I'm afraid, but I will try and speed up a little bit. They fully reconstruct events here. So you have two Bs produced at the upsilon 4s. One of them gets fully reconstructed to d pi event here. So you know fully the kinematics then of the side where you have your d to tau nu decay. And you have your tau decaying to a single lepton, and you have these 3 neutrinos. So using the heavily constrained kinematics, and the shape of the events and the lepton momenta involved, you can distinguish these between the regular muon decay or electron decay of the B and the tau decays. And this does some, I think this is a neural network. Yeah, it is a neural network, not a boosted decision tree. And the signal here is this tiny red piece, but using this multivariate discriminant, the signal piles up here close to 1. All the backgrounds are here at lower values. This is the normalization in the sort of turquoise hatch. And then there are combinatoric backgrounds, and then some higher D-star resonance stuff as well, where you're missing particles. But then you can select out that little region. And because if you've really reconstructed everything in the event, you'll have nothing in your calorimeter at all. And the true signal piles up at 0 extra energy in the calorimeter. Of course, there's some photons flying around, and you end up with a few hundred MeV extra energy some of the time. from initial or final state radiation. But it's a clear signature, and this is the signal over background that they have for D-star tau nu. And then there's also a semi-leptonic tag version where it's not quite as clean, but you have much higher statistics, so you gain something. Now, LHCb also do make measurements of these B2C tau nu, and they exploit the very good vertexing that they have. This highly boosted Bs into the acceptance of the detector means that they can reconstruct not only the secondary vertex where the B decays, but also the tertiary vertex where a D star sorry, this is the odd looking, where the D decays here and the D star, this is the slow pion from the D coming directly from this vertex. So they can reconstruct these 3 different vertices, and they can distinguish between the tau and the mu by looking at the amount of missing energy. However, their little red signal here is atop a very large background. And this green in particular is where you have D double star decays, where you're losing some particles in the detector, and this is very hard to understand. So this is quite a model dependent measurement and very difficult measurement. But if you put all this together, you have a set of measurements, starting with the Babar one here, various Belle measurements, and then 2 LHCb measurements here. If you combine them all together, you get this 1 sigma region in dark red and this 3 sigma region here. And the standard model, including the uncertainties on the standard model, is this small cross here. So this has stayed over 3 sigma for a very long time. And of course, there's some scatter in these measurements like we had before. Sri Hari, and I'll come back to this, may want to just believe these 2 measurements, but this has held up over essentially 3 different experiments measuring this, and it's still significantly disagreeing with the standard model. So going back to these global fits, it's the same paper that I showed earlier. You can add in these RDD and RD star variables, and you can fit again to these Wilson coefficients. So here you have V minus A violating lepton number, not lepton universality violating Wilson coefficients versus a new universal one as well. And with that, you can actually fit all the data together. So the green is the B2SLL, and then if you include the RD, you get to the red region, and that's a significant disagreement. Again, many standard deviations away from the standard model. But of course, what is the underlying physics interpretation of such a scenario? Now, I'm not going to talk about this in great detail, partly because I'm not expert and partly because I'm a bit short of time now. So you could think of tree level solutions where you add flavor changing neutral currents by having additional gauge bosons with off diagonal couplings. So what we'll call Z primes, but there tend to be strong collider constraints for such tree level solutions to all of this. If you just look at B2SLL loop, you have many, many possibilities. Scalar vector fermions, 2 Higgs doublet models, Z primes coupling to top, and a doublet of these lepton quarks. But if you try and do everything together, one beyond the standard model scenario sort of stands up, and that's lepton quarks or vector lepton quarks, where you can have this lepton quark in the loop, where you'd have a tau and this vector lepton quark mediating your B2S LL transition, and you can also have that, as I've shown before, leading to this tree level effect. And giving it's got preferential couplings to the 3rd generation, you can kind of escape other collider bounds on the lepton quark because of this. But there's no additional Higgs sector being added for this, so the UV completion's a little difficult. I don't want to talk too much about this, but there's a very nice review that Gino Isidori gives. The one I saw was at Beauty. I think he's given it elsewhere, which really digs into these different possibilities. And essentially, he advertises what I'm going to say in the last little bit of my talk. So, Ayan, how much more time do I have?
10 minutes.
Okay.
Or, okay?
Yeah, that's kind of okay. I'm going to have to skip a couple of things about Belle II, but that's okay.
But you can take a little bit more time also, no problem.
Okay, okay. So before moving away from the anomalies, I should say something about the other anomalies that are around, because they are often said to be able to be fit by this pattern as well. Sorry. So the other mainstream media physics result or particle physics result this year has been G-2, which has this very impressive 4.2 sigma standard deviation between the generally accepted standard model prediction, I should say, and the new measurements. And this effort to make this new G-2 measurement is hugely impressive. And anyone interested in experiments and what they've done to do this in terms of the homogeneity of the magnetic field and the intense source of muons and the careful analysis, blind analysis that they do to measure this is a very interesting and extremely impressive endeavor. And that's also true of the theory, which is producing this number. Now, this plot down here gives the various predictions for this anomalous moment of the muon from different theoretical approaches. All these in blue are from lattice QCD, ab initio calculations from lattice QCD. And these come from interpreting other data in terms of dispersion relations to work out this hadron vacuum polarization. So that's a talk in itself. But these two down here are taken as a state of the art, which rely on E plus E minus measurements to light hadrons and tau decay. And this gives the world average number that I show up here. But the eagle-eyed amongst you, and you probably have read about this, there is one of the lattice calculations which has the smallest uncertainties, which is not that incompatible. This orange band roughly corresponds to where the experimental value is, so it's just less than 2 standard deviation effect. And as you see, all these lattice numbers are scattered around all the way between this dispersive relation number and the experimental result. So I must say I'm no expert on lattice QCD, and I don't want to discuss the virtues or lack of these particular measurements. I can't comment on that, but I do feel that this is going to really muddy the waters on this G-2 anomaly for some time until the lattice community can fully agree on whether these uncertainties are good, or how other collaborations can test this. So this is a somewhat unfortunate state of affairs, given the great fanfare this was announced with. I want to dig into this. I'm a little less optimistic than I once was, but it takes nothing away from the experimental effort that's gone in to make this measurement. But there are other anomalies which are quite interesting as well. One is this Cabibbo angle anomaly, where you are measuring the coupling of the up quark to the strange quark. And if you take the sum of these 3 CKM matrix elements, it should come to 1. It's a unitary matrix, but it's 3 standard deviations away. And there are various ways of measuring this. You can measure VUD and then work out what VUS should be, because VUB is so tiny it has little impact on any of these measurements. It's really about VUD and VUS. You can measure it in kaon decay, or you can measure US directly in kaon decay, or you can measure it directly in tau decay. And you see that there's a trend amongst these, rather suggestively plotted in this way. And of course, this buys into the idea that there might be something to do with lepton universality. This is measured in taus here, this is measured in mu's, and this is measured with electrons. And these are kind of largely theory dominated in their uncertainties, but the tau measurement can certainly be improved experimentally, and that is on the list of things that Belle II will do in the next decade. Also with the taus, there's some tension between a tau decaying to a muon and 2 neutrinos from what you'd expect from the standard model. And this is shown in this 2-dimensional plot, that the 0, 0 is the standard model here, but the central value sits off a little bit to higher values for tau to mu nu nu. And there's also in hadron physics, there's a hint of an excess of dielectrons at large invariant mass. But with my experiment, and these of course can all be linked to lepton universality, but with my experimentalist hat on, anything that's just 2 standard deviations, it's 1 in 20 measurements should disagree by 2 sigma. So we should always be careful. So the future, I like Mr. McCorber, something will definitely turn up here, but it's a matter of when. So the LHCb experiment is currently being upgraded for the start of run 3, which should begin early next year. And they have a timeline to continually upgrade their detector well into the 2030s and finally accumulate around 300 inverse femtobarns of data when they currently have 10, so 30 times more data. This is done by essentially surviving at higher luminosity, and they've had to upgrade their detector significantly. So there's new silicon detectors downstream of the magnet, and then upstream of that, downstream there's the silicon, and upstream there's a new tracker, but no upgrades to their calorimetry, so they'll still have the same limitations as before. They are now reading out all their data at 40 megahertz, so the trigger's purely in software, which is very good for hadrons, but not so good for leptons. They were already very good for leptons. So this will continue to have a huge impact and will be the leader for some time in the years ahead. But I want to spend what time I have talking about, so I should also say CMS and Atlas are forever putting more emphasis on B physics too, and they will come with results, but they have not quite as severe problems with electrons as LHCb does, so that the lepton universality will be quite interesting when they do this. But it's a very busy environment, and again, it's much harder than what's possible at Belle II. So Belle II builds on the success of the Belle and Babar experiments, which ran through the first decade of this millennia, where they collected around 1.6 inverse attobarns of data. There are many significant achievements, some related to these B2SLL events that I talked about, types of decay. There was a Nobel Prize for confirming the Kobayashi-Maskawa mechanism for CP violation. And of course, this excess in B to D star tau nu was also, after running, discovered by the very careful analysis. So Belle II is essentially, you can never have too much of a good thing, and it's an attempt to collect 50 times more data than Belle, so around 50 inverse attobarns of data. So what would it be able to do that LHCb isn't able to do? So LHCb has this huge statistical advantage. So this 1.6 inverse attobarns corresponds to around 1.5 billion BB bars. So it's a much smaller data set in comparison to what's possible at the LHC, but it can be a very high luminosity machine to partly compensate for that. And it has much lower backgrounds because you're still producing, just like Argus, a B0, a B0 bar, a B plus, and a B minus, and nothing else. So it's a very clean environment to work. And hence you have very high efficiencies, and you're efficient for neutral particles as well. So we can measure all of these anomalies with K shorts as well as charged particles. We have this well-constrained kinematics, unlike what you have in proton-proton collisions. You have not quite as good vertexing because you don't have that huge boost. We have some boost because it's an asymmetric machine. It has a very small primary vertex though, which helps. It doesn't produce all types of B hadrons. It only produces B0 and B plus. Has very good tau physics, which I won't talk about, and this flavor tagging efficiency I also won't talk about today. So how this is being done is really an upgrade to the accelerator. It's not really to the detector. So this is the master formula for luminosity. And there are 2 parameters I'd point you at. One is the beam current. So you can increase luminosity by boosting the current, or this beta star function here, which is basically how small you can make your beams. Now, the brute force approach of increasing the currents would actually melt the beam pipe through synchrotron radiation. So the second approach is taken where we've squeezed down how we collide our beams. So the green and the red are the electrons and positrons bunches colliding, as they were in Belle on the left, and as they are being collided now in Belle II in Super Keck B. And they have this hourglass shape, which essentially squeezes down this region to a few nanometers, tens of nanometers, where they collide, and this allows for a very, very small beta star function, and will get us to these very high luminosities, a factor of 30 more than was there at Belle, so we can integrate this large sample. So I'll skip over the accelerator details, but you can ask me about that. But we're still a long way from that. This is a plot I took from the running page yesterday. We've only got to 160 inverse femtobarns. We still have a smaller data set than Belle, but by next summer, we hope to have accumulated something of similar size. But as you can see, there's a good upward trend in terms of how much luminosity we're collecting. But there are significant problems with background in the detector from the very high currents and the optics to squeeze down the beams. I can talk about this for a long time, but I won't in this forum. But the long-term plan, so we're down here in 2021, the blue line is the integrated luminosity, the red is the instantaneous luminosity. We are still some way from our target of getting up to this 6 times 10 to the 35 instantaneous luminosity. We're still down here. Actually, this is slightly out of date. And there are some upgrades that are required for both the accelerator and the detector to get there. So our data will only come within the next 10 years. It's a slow process of accumulating this. So the Belle II collaboration is global, with about 5% coming from India. It's 1,000 physicists, so it's a bit smaller than the LHC experiments. And the detector is much more standard than LHCb. It has all the things that one normally expects from a general purpose detector. It also has that hadron ID ability. It's been improved for Belle II with a time of propagation counter, and also the silicon is much improved as well. And various bits of the readout and other things were redone. But the larger upgrade was to the accelerator rather than to the detector. So even with the small amount of luminosity, we've actually got a measurement that's of quite great importance to what I've been discussing in this talk. And this is B to S nu bar, which goes through the same kind of penguin diagram as those B to S LL anomalies. But here, of course, you'll be summing over all the possible neutrino types. So your new physics that might be contributing to the lepton flavor lepton universality violation that one sees in RK, for example, would impact this in measurement. So that the standard model would expect, the standard model prediction would change depending on the new physics. So this is a correlating observable. And even with a very small amount of data and some extensive use of machine learning algorithms to identify a signal using, again, data-driven techniques to do this, you can use a succession of boosted decision trees to actually isolate the signal. So the signal is here in pink. And an upper limit's been set with just 63 inverse femtobarns of data, which is competitive with previous measurements using these combinations of boosted decision trees. So with the data we will get by next summer, and also reanalysis potentially of the Belle data, we should be getting a very interesting measurement because it's getting very close to the standard model value. So whether we see an enhancement or a suppression of this would tell us a great deal about what might be going on in the B2SLL anomalies. Then finally, or not quite finally on the B2SLL, RK star and P5 prime, the important distinction that's there between LHCb and Belle II is that we're highly efficient for electrons, and we also have very good resolution by exploiting the constraints, kinematic constraints that come from the knowing the E plus E minus collision energy and its momentum. So here on the left, we have a Belle measurement of K star LL, but for both electrons and muons. And it's roughly the same efficiency. It's a little lower for electrons, but but not as dramatically as LHCb. And the resolution and the background levels are very similar. And this allows P5 prime to be measured for both electrons and muons. And a very robust observable would be to take the difference between P5 prime, so-called Q5 prime, between the electrons and muons. And there, some hadronic uncertainties cancel out. And also you expect new physics in the muons, but not the electrons in most of the new physics theories. So this is a Bell measurement, but we will do much better than this as we accumulate more data. But much more is required, around 10 inverse attobahns of data, before we'd have something very meaningful on this. So these are the projections where we push down to around 10% measurements with 5 inverse attobahns, and then a few percent measurements with the full 50 inverse attobahns. And again, this Q5 parameter with the difference between electrons and muons, it's kind of key, but we need very large data sets to do this. And unfortunately, we're just here at the moment where we're just starting to see a signal poke above background with our 63 inverse femtobarn data set. Of course, I should also talk about B to C tau nu prospects at Belle II. I recommend Florian Bernlocker's talk at APS for a full discussion of this. These plots are busy, but they show LHCb on the left and Belle II on the right, where over the next 10 years, we're pushing down the measurements, particularly of RD and RD star, to a few percent. Some of the lines here on the Bell plot are overlapping with one another. And we'll have something more interesting to say on this, particularly on Belle II, within a few inverse attobahns, because we can average together all of these measurements. So I think the situation with B to C tau nu will start to become clearer, but I must be a little cautious. And something I mentioned earlier, there is some skepticism around these results based on the fact that the most recent measurements from LHCb and from Bell are actually pretty much compatible with the standard model. So there is some tension amongst these results. It's not great yet, but it desperately needs more data and more measurements to sort out what's going on. So to conclude, getting to my Dickens, I'll take a tale of two cities. In some ways, it was the best of times. We have many measurements in B decay showing deviations from the standard model, and many are related to a single source, lepton flavor universality violation. And we seem to see perhaps consistent new physics models can accommodate them. But it's also the worst of times in that there's no single 5 sigma observation in a robust observable. There's no corroboration between two experiments, and new data coming from both LHCb and Belle II requires patience. It's going to take several years before we'll be able to resolve the status of the anomalies. So that's it. Sorry, I overran.
Thanks, Jim. It was a great talk, and it was yeah. Thanks for this very detailed story, and it was quite. We have some good idea now, hopefully. So some questions now.
Hi, can I ask a couple of questions?
Yeah, sure.
Okay, yeah, just this first point, it was the worst of times. Isn't B to K star LL, isn't that single one more than 5 sigma? Or
No, none of them. None of them are 5 sigma.
So
only
close,
this,
though, right?
only the global interpretation. Once you put all the measurements together and you do the Wilson coefficient analysis, you'll get something that's 5, 6, 7 sigma. So there is a consistency.
K star LL, the angular distribution, that alone is how many sigma is that?
Three, just over 3 sigma.
Right.
So one expects an LHCb update on this at some point. It's been due for some time. They've got more data. That's just run one data. It's not all the data. But it's not going to be enough. It's not going to be enough to push it to 5 sigma. It's not that big an increment.
So one other thing that about this, I guess the RK star, I think you said that you would expect a larger deviation in the muons in most models, But I thought you also said that the experimental mu is the one that's showing the deviation.
Yeah, that's
Did I
right.
gather that correctly? I mean, these are
Yeah.
at odds, right?
Yes. So if you do a branching fraction measurement from the LHCb data, it's the electrons are spot on the standard model prediction, the muons are low, but the uncertainties are larger then because it's a branching fraction. You don't benefit from the ratio, but it looks like the electrons are correct and the muons are low.
Yeah, I suppose it's just a prejudice, and there is no real, experimental justification for why we should think that deviations in muon is going to be more than electrons.
No, there are. I have seen talks on this. There tend to be better constraints coming from other measurements if it were in the electrons.
I see.
So it does make sense that it might be in the muons, and it's related to second and third generation rather. So it's actually relatively, these models that you have to build, they pretty much got to have minimal coupling to the first generation to escape things from the LHC essentially. Otherwise you'd have up-down quark couplings and things. So they've all got to come in loops, and so it's basically second and third generation is where you'd expect to see deviations.
Oh, so it is, the experimental results are consistent with that.
Yeah.
Yeah, okay, I thought I got it.
Sorry, no,
So,
maybe.
yeah, okay. No,
So,
I think I misunderstood. Okay, yeah.
So even that Cabebo angle anomaly, you put the new physics in the muons and the taus, and you can explain it. So that's actually quite an interesting one, because that's also at this 3 sigma level, and then these are very well understood measurements essentially. But so that's something that I think will be talked about more and more in the years ahead.
Yes, so you showed this B2 SLL and then also the tree level B2 D star tau mu with this leptoquark kind of an explanation, I think. And so putting them together, a single mass scale would do it for both of them, or do you have to assume different things, or what?
Yeah, so my understanding is you can do it, and again you tweak the couplings so it's very much second and third generation only. You only have minimal couplings to first generation, and you would have to have a sort of TeV range leptoquark to do this. And there are quite a few papers which I probably, if I'd had more time, I would have looked at, where they then talk about complementary signals that would be there in high PT physics if you have such a leptoquark. I can't remember what they are off the top of my head, but I have seen talks about this. So there is some complementarity there. But the problem that people always talk about is this UV completion, because you're not adding additional, you need to add additional Higgs sector to make it stable in some way, and that's not there. And I think people have a hard time. There's talk of Patti Salam and things you can do, but I'm out of my comfort zone when I start thinking about all of this.
Okay.
So yeah, actually I have a related question. Sriri, can I ask, or you are done?
Please go ahead. No, I have one more, so if there is time, I can ask later.
Oh, no. Okay, then, okay, maybe, okay, but my question is slightly related to what you're asking. So this, and also what I was asking before. So this four quark operator is something that we must have seen, and we can of course see it, but as you said, it is only makes sense if it involves higher generations. But then my question actually is that, is it because it involves higher generations, is hard to directly see it? Otherwise, I don't see why it cannot affect in general some Higgs decay also from effective field theory point of view. It can, but because it's involving higher generations, it's harder to. It will be harder to see it in other processes.
That is my understanding, that you can escape. So if you are trying to, in B2SLL, if you're trying to use a Z prime, where the constraints are actually pretty stringent in terms of the LHC, you can do it if you say, oh no, it's barely coupling at all to anything other than the third generation, and you just put it to be coupling to the top and your leptons, and then you can say, yeah, you can escape all the limits, but you have to make it very much generation specific, right? Or there'll be some coupling between the second and the third, but there'll be limited coupling to the first, and you can escape it. But if you say that there's going to be like some universal coupling amongst the generations, it just won't work. Yeah. So you've got to say there's something special about the higher, the second and third generations, particularly the third generation.
And this is precisely what is making it harder to, even if you look at the differential Higgs decay cross section in certain processes, it'll still be hard to get enough background, enough high luminosity to see such effects there.
Yeah, yeah. So, so things I've seen have been talking more about. It's probably Higgs to tau tau. I think you can see something, and there's. I know I'd have to look back. I remember seeing a talk. Maybe in Gino's talk, actually, there is some discussion of this where he has the potential signatures that are there. And then, of course, now people are getting interested in this excess in CMS at high dilepton mass in the Drouin cross-section. And okay, it's 2 sigma, but people are now starting to wonder whether something is going on there. That sort of then would go against a lot of this, though, because that seems to be a first generation thing then. So I'm not sure how they square the circle with that.
Unless it's somehow in the loop, that it is affecting in the loop. When it's a higher dimensional operator, sometimes it can,
It's anyway. This is, all we can do as experimentalists is just measure as many things as we can and as precisely as we can. And ultimately the gold standard it will be if LHCb and Belle II agree on all these things experimentally, and they are very different measurements. We have very different problems in the 2 experiments, and it would give great confidence if in 3 or 4 years time, if we all agreed on the value of RD and RD star, then I think everyone would accept that something is going on there. And it will take longer in RK and RK star, but again, I think that will be a similar situation where if both experiments see the same thing, it's unlikely to be the same mistake, given that the experiments are so different. And for example, in the beta C tau nu, LHCb's problem is the background, whereas our problem is really just efficiency and signal extraction, because our rates are lower. But we're, it's a different set of problems.
Well, Srihari, you had more questions?
Yeah, I have just one more if there is time.
Oh, sure.
Yeah, so there was one which I thought was the C9 interpretation, C9 C10 prime, I think, for B to D star tau nu also put into the thing. I missed there was a C9 prime U.
Yeah, this one. Yeah, okay, sorry. I was getting stressed about the time. This one.
Yeah,
so
this one. So what does the C9
so
U and C9?
So that means this is standard model like in terms of weak couplings. So this is universal.
Which is V
so there's
-8,
some
right?
alteration to. Yeah. Well, this is also this is just C9. C9 minus C10 is effectively V minus A in this, as far as I understand it. So this is just adding more left-handed current. Of some type, or less left-handed current.
Yeah.
But to do all of this together, you've got to modify C9 differently in the different generations.
I see.
So so this one will be affecting just, I guess it's generations 2 and 3, and this will be affecting 1, 2, and 3. And by doing all of that, you can fix this up. So
so the mu subscript there means muon, is it? Like at the x-axis, the C9 mu. Is that made?
Yeah, I think.
Yeah, it's added in only.
Yeah,
for
I don't. I guess I get.
Maybe.
Yeah, so this would be affecting the tau and the muon.
Okay.
And the electron.
Yeah, okay, makes sense. All right, okay.
And you can get this, but I'd have to. Sorry, I didn't read in detail. This is a new paper post Morillon.
Okay, all right.
Which where so this is Sebastian and collaborators, Descogeno. So who's one of the leaders in all of this stuff.
So you are convinced that we are seeing new physics in all of this?
I slowly get more and more convinced, and I think the RK was certainly a step in the right direction. It's a variable which is, I think, very reliable. The measurement that would really convince me, which I think is a long way away, unfortunately, is it's this one. If you see in the differential distributions a real significant difference between muons and electrons, that would be really quite convincing that there's some new physics there, because and then you're taking the difference, so you're taking out a load of hadronic uncertainties in doing that. The only thing that can be driving such a difference would be some new physics going on in that penguin loop. But there are other things that can happen. As I said, if LHCb and Belle II converge on the same value for RD and RD star, then I see nothing. I don't see why anyone would doubt these measurements. There has to be something happening there as well. And RK is, as I said, a robust variable, but you'd like it over 5 sigma, and you'd like to see it in Belle II as well, where there'll never be a doubt about the electrons compared with the muons. Where there's always people always worry however much work LHCb do on their electrons. People are always going to point at that plot where you have the huge background compared with the muons and say, do you really understand this to 15%? Now, that I think is really unfair, because I think they've done a good job. And I'm an ex-LHCb person, so I'm probably a little biased too. But I think when this finally comes, when they've got the extra 75%, and these numbers are significantly lower than RK, if these come out low as well and with some significance, then I think it's starting to look relatively convincing. But again, everyone will say it's the same electron reconstruction. So if that's wrong, but I don't. So yeah, that's a hard one without Belle II. But Belle II just needs a huge amount of data. It needs tens of inverse attobonds to do this.
But given
we're
that
just a statistical disadvantage.
Yeah, given that JSI is a control thing, it's hard to see how it can go wrong, I suppose, right? As you said.
Yeah.
Okay.
But okay, so to go with the naysayers, the thing you must look at then is this background underneath. Okay, what they're saying is they know this shape of this blue stuff really well. Yeah, so if, for example, you've got this wrong and you've bled in 10% extra background here, that means your electron signal would then agree with the muons, and RK is 1. Okay, if you've got the background wrong, then you look at J psi, there's no background. So you can't, it's not, but it's hard to know how they'd get that wrong. That's as from an experimentalist point of view. But this is the concern that you have, that this is not a pure signal background, signal. It's not as high purity measurement. So therefore you have scope to, just parameterizing your background incorrectly can change your yield.
Sorry, if you get this blue thing wrong, then your JSI is going to go wrong, right?
No.
No.
This is purely there for this is only there for the BKEE signal, because, sorry, there is some background down here, but you can't see it. You can't even see this combinatorial, because it's just so much signal over background. So there's no way they can even control the level of the background because it's swamped by signal.
I see.
Of course, there are sidebands and all sorts you can use, and they do this, but yeah, I'm just telling you what the doubt is. I don't really believe that's a problem, but it's just a very different scenario to the muon measurement, for example. Just looking between left and right here, you can see how pristine this is in comparison. And it's all down to these issues of the Bremsstrahlung.
Okay, great.
Now, if you'd listen, so LHCb, if they had millions of dollars, they'd upgrade their ecal, but no one has millions of dollars anymore. So it's I think they could build a very nice calorimeter for like $100 million or something, and then they could probably,
for possibly the only signature of new physics, doesn't the world have $100 million?
It did in January 2020. It doesn't anymore. I don't know. I don't think India is going to be contributing to that effort, I'm afraid. So yeah, I know. But now it's a bit. There is talk for their future upgrading their calorimeter as well.
I see.
You should hear Sheldon Stone on this.
And Belle is going to say something about this at some point, I guess, right?
Yeah, but we require tens of inverse atom bonds. I think we'll have something interesting at around 10.
I see.
I think before that we won't have the statistics. We just and then
Jim, are you there?
Sorry, I lost the connection also. Yeah, I cannot hear Jim.
Yeah, I think he's having some connectivity problem maybe. Yeah, anyway, I think we need to end too.
Yeah, thanks for entertaining my many questions. Sorry, I might have asked too many.
I think we were nearly
so
done
I started
anyway.
the recording. Yeah, I think we have to stop now anyway. It has been quite long.
Okay.
So
yeah.
So thanks Jim again for this very detailed talk, and thanks everybody for participating. So goodbye, and then have a very nice evening, and Jim, see you around soon.
At some point via Zoom. Okay. Thank you.
Okay.
Bye-bye.
All right. Thank you very much. Bye.
Bye.
Bye-bye.
Bye.